Welcome to the PV online course on grid-connected PV system. This chapter deals with solar radiation. In this particular teaching unit, we will learn how to calculate the sun's position in the sky. The position of the sun in the sky is determined with the help of the sun azimuth angle and the sun elevation angle. The sun elevation angle, gamma s, is the angle between the incident solar radiation and the horizontal plane, as shown by the yellow area in the diagram. The red area in the diagram describes the sun azimuth angle alpha s. It is the angle between the north direction and the projection of the sun center onto the horizontal plane. North corresponds to 0 degree and south to 180 degree. If the sun position in the sky is in the east, the sun azimuth angle is 90 degree. If it's in the west, the sun azimuth angle is 270 degree. It is important to understand the geographic coordinate system of the Earth in order to correctly calculate the sun position. The Earth is divided into 180 latitudes. The latitude specifies the north-south position of a location. The latitude ranges from 0 at the equator to 90 north or south at the two poles. All latitudes form a line parallel to the equator. Hence, these parallels are lines of constant latitude. On the other hand, the longitudes are specifying the east-west position of a location. They range from 180 degree west to 180 degree east. Meridians are lines of constant longitude. The prime meridian of 0 degree is located in Greenwich, near London, in Great Britain. But how did it happen that the prime meridian is located in Greenwich? Now, in the 7th century, the British King Charles II was worried about his navy, as ships got lost due to inaccurate navigation. For this purpose, the Royal Greenwich Observatory was founded in 1675. The observatory was built on a hill viewing the harbour of London in Greenwich. The location of the observatory determines the prime meridian, the longitude of 0 degree. From this line, all east-west positions of the Earth can be determined. The prime meridian is not only indicated by a letter on the wall, but also by a metal stripe on the ground of the central court of the observatory, shown in the left picture. The second issue regarding accurate navigation was timekeeping or accurate time measurements. For this purpose, the red ball had been installed on the roof of the observatory, as shown in the central photograph. It could be observed by all ships in the harbour. Always at noon, the red ball or globe was dropped from the top of the mast. The astronomers knew that an optical signal would be more accurate than an acoustic one. This allowed the captains of each ship to set their clock to the accurate Greenwich time. The third issue was the accurate determination of the position of the ships. During that time, this was done with the help of the time and the position of the sun or the stars at night. The cartography of the stars was done with the help of accurate telescopes, shown in the photos on the right. This picture illustrates the movement of the Earth around the Sun in the center and explains seasonal variations in irradiation. The rotational axis of the Earth around itself is tilted by 23.5 degree with respect to the ecliptic, the plane which is formed by the movement of the Earth around the Sun. This has the effect that in June, in summer, when the northern hemisphere is facing the sun rays fall on the Earth on a smaller area than in wintertime, and the irradiance on an horizontal plane is stronger than in winter. Furthermore, the air mass is smaller than in winter, resulting in a higher irradiance as well. On the contrary, in December, in winter, when the northern hemisphere is tilted away from the sunlight falls on a larger horizontal surface. In other words, the sunlight is more diluted. Hence, the irradiance is weaker. Furthermore, the sunlight travels a longer path through the atmosphere. In other words, the air mass is increased and the irradiance is even weaker than in summer. The effect in the previous diagram can be accurately determined with the help of the declination. The declination, delta, is the angle between incident solar radiation and the equatorial plane as shown in the diagram. It can be calculated with the help of the formula in the red frame and is given in degrees. The number n indicates the day in the year, with January 1st being n equals 1. On June 21st, with n equals 182, in the Earth's axis fully tilting the north hemisphere towards the sun, the declination reaches its maximum with plus 23.45 degree. As opposed to this, on December 21st, when n is equal to minus 10 or plus 355, the Earth's axis is fully tilting the northern hemisphere away from the sun. In this case, delta is negative, the value is minus 23.45 degree. On March 21st and September 23rd, the angle between incident solar radiation and equatorial plane is 0, and hence delta is 0 degree. In order to calculate the sun position accurately, we need to understand the concept of solar time. Firstly, the local mean time, LT, is the time everybody knows. It is the time you can read on your clock or watch on your smartphone. Hence, the local time is the clock time. However, it is an artificial standardized time based on time zones. It allows people in different locations to use the same time, but it is not related to the real sun position. On the contrary, the local solar time, LST, is the time according to the position of the sun in the sky. It is the time which was determined by humanity in historic or ancient days when solar clocks were used. We need to know the definition of solar noon. Solar noon is the time when the sun reaches its maximum height in the sky on a specific day. The sun is exactly in the south on solar noon, of course only in the case of the northern hemisphere. The local solar time, LST, is defined in such a way that LST is exactly 12 at solar noon. A solar day, then, is the time from one solar noon to the next. But how do we calculate the solar time, LST, from the local time or clock time, LT? The question will be answered in the next 8 slides. The solar time is correlated with the hour angle omega. The Earth rotates 360 degrees in 24 hours, which is equal to 15 degrees per hour. This means that 2 locations with a difference of 1 hour in solar time have a longitudinal distance of 15 degrees. The hour angle omega is defined as follows. It is the angle between local longitude and the longitude of the location with solar noon and can be calculated with help of the formula given in the red square. Omega in degrees equals LST minus 12 hours in brackets multiplied by 15 degrees divided by an hour. The diagram displays the concept of the hour angle. In this example, the hour angle would be 60 degrees. As already stated, the clock or standard time LT is based on time zones. The map below shows 3 different time zones in Europe. The time zones are linked to standard meridians. UTC stands for Coordinated Universal Time. The meridian of UTC is the prime meridian defined by the location of the observatory in Greenwich. The Central European Time, CET, is 1 hour ahead of UTC. In the legend of the map, it is marked with UTC +1. It is the pink or violet zone. It refers to the meridian at a longitude of 15 degrees east. Within a time zone, solar noon at different locations will occur at different clock times depending on their longitudinal distance. In the map, the Central European Summertime CST as solar noon of different cities are shown for June 21st on 2021. Solar noon was 12:39 in Belgrade, 13:34 in Cologne and 14:16 in Madrid. The CET time zone has a very large east-west extension. Due to the large variations between LT and LST within a time zone, it is important to correct the local time with a correction factor LC, taking into account the local longitude and the standard meridian of the local time zone. As already stated, 15 degrees of angular rotation on the Earth is equal to 1 hour of time, or 1 degree of angular rotation is equal to 4 minutes of time. The formula given for LC calculates LC in minutes. Please note that longitudes east of the prime meridian are positive valued, whereas longitudes west of the prime meridian are negative valued. Added to the local time LT, the correction factor LC brings us closer to the local solar time. However, we still need to consider another fact. This brings us to the time equation. This equation is based on the fact that the angular velocity of the Earth's rotation around the Sun changes periodically, which is due to two facts. First, the Earth moves around the Sun on an elliptic orbit. This is explained in the graph shown. At the shortest distance to the Sun, the perihelion, in January, the Earth is at its fastest. At the longest distance to the Sun, the aphelion, in July, the Earth is at its slowest. The second fact, which influences the angular velocity of the Earth's rotation around the Sun, is its inclined axis with respect to the ecliptic. Hence, the Sun appears to move slower or faster depending on the Earth's angular velocity, and the length of a solar day is not equal to 24 hours. Nevertheless, the mean solar time during 1 year is indeed 24 hours. But the apparent solar time on a particular day varies plus/minus 15 minutes. Now, the equation of time describes the offset between mean and true solar time for each day of the year. It is given by the formula in the red box, and its units is in minutes. The equation uses the variable b equals 360 degrees divided by 365 multiplied with n-1. N being the number of the day in the year. Remember, January 1st is n equals 1. This diagram displays the equation of time. The x-axis represents the day of the year. The y-axis shows the time difference between apparent solar time and mean solar time in minutes. At the 4 indicated zero crossings, the apparent solar time equals the mean solar time. Values above 0 indicate that the true solar time is ahead of the mean solar time, and values below 0 indicate that the true solar time is behind the mean solar time. Only at the 2 minima and the 2 maximum, the day length of the apparent solar time equals 24 hours. All these facts lead to the phenomena of the analemma. The analemma displays the position of the sun in the sky viewed from a fixed position at the same clock time for every day throughout the entire year. It depends on the declination and the time equation. The diagram shown here shows the position of the sun viewed from the shore of the Rhine River in Deutz, Cologne, in western direction, always at 3 p.m. or 15 hours, winter time, in 7-day intervals. The other diagram shows the corresponding point on the time equation. It can be seen that there is a direct correlation between the time equation and the analemma. This leads us to the final equation, which allows us to calculate the solar time LST from the local or clock time LT. In winter time, LST is LT plus the longitude correctional factor plus the time equation. In summertime, the solar time is the clock time plus the longitudinal correctional factor plus the time equation minus 1. Of course, all values are given in hours. Finally, we are able to calculate the sun azimuth and the sun elevation. The sun elevation angle gamma s is given by the formula in the upper red box. It depends on the declination, the latitude and the hour angle. Please note that the hour angle is directly correlated with the solar time and hence also depends on the longitude, the clock time and the time equation. The sun azimuth angle alpha s can be calculated by the two formulas in the lower red box. It depends on the sun elevation angle, the latitude and the declination. Please note that the formula is different for solar times in the morning, before noon, or in afternoons, as indicated. With these equations, we are able to calculate the position of the sun in the sky for any location on the Earth and any time. This diagram shows the sun paths for Cologne during the entire year. The x-axis shows the sun azimuth angle in degree, the y-axis sun elevation angle in degree as well. The lowest sun path occurs during January and December. The highest and also the longest sun path occurs during June and July, indicated by the red curve. Furthermore, the analemma for 4 different hours is shown. The analemma for 15 hours is the same as the one previously shown with the skyline of Cologne. This leads us to the summary of this teaching unit. Firstly, the sun's position in the sky is measured by its elevation angle and its azimuth. Changes in the sun position in the course of the day are due to the Earth's rotation around itself, whereas seasonal changes are due to the Earth's tilted axis. The solar time is different from the clock time because of the following facts. First, the difference in latitude to official latitude of the time zone. Second, the daylight saving times. Third, the elliptical orbit of the Earth. Fourth, the inclined axis of the Earth. Variations in the length of a solar day are described by the equation of time and can be observed in the phenomena of analemma. I thank you for your attention.